Okay, today we're going to learn about why a bond is covalent or ionic or whatever. So far we've just been saying yes, it happens that way, but why? So once again, I don't like the way the book covers this, so I'm going to use a PowerPoint that I made myself for a few slides here. The key property, and this is one of our periodic properties that we didn't talk about last chapter, but it's another one of them, called electronegativity. Um, Electronegativity is a big ugly word, but it's a measure of the attraction of an atom for electrons. Yeah, we have a lot of those already, don't we? Um, so yes, this is another property that describes how an atom attracts electrons. You'll recall ionization energy measured that attraction by removing electrons and forming positive ions. Electron affinity measured the same attraction for electrons, but it measured it by feeding electrons to the atom and forming anions. Both of those were good in terms of ionic compounds. If I want to talk about the attraction of a sodium atom, I'd probably talk about ionization energy, losing electrons. If I wanted to talk about the attraction for electrons of a fluorine atom, I'd probably talk ionization energy because it forms anions. But what about if you're forming covalent bonds? They're sharing electrons. Yes, these atoms are still attracting electrons because they got a positive nucleus, but I can't really discuss that in terms of ionization energy because no one's getting ionized here. We're just sharing electrons and forming a covalent bond. So we make up another property called electronegativity. And again, it exactly is the same thing. It measures how well is each atom attracting electrons. But now we're measuring it by how they attract the shared pair of electrons. Now, it's going to follow the same trends as before. So I'll show you a graph here. You don't have to memorize this graph. There's breaks in the graph because we don't have electronegativity values for the noble gases because they don't form covalent bonds. So here's hydrogen, and then lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. None for neon. Then we come back to sodium and go across its row. Then we go to potassium across its row. Notice as you go across a row, the attraction for electrons is increasing, just like we saw last chapter. Again, going across sodium's row, attraction is increasing. Going across potassium's row, if you look at your periodic table, it's increasing, but things get a little chaotic in here. What's going on there? Those are your transition metals. And you got some weird rearrangement occurring from place to place, and the transition metals get weird. You'll find these trends, we talk about, yes, going across, they get bigger and whatever, but that's a general trend. It's not like an absolute truth. So you'll find that even though the general trend is increasing across a periodic table, there will be exceptions, and we'll look at that in a moment. Notice going down a column, you've got fluorine, chlorine, bromine here, and so on, iodine. Going down the column, you're decreasing. But that makes sense. As you go down the column, atoms are getting bigger, the attraction is getting weaker. Here we see it with hydrogen, lithium, sodium, potassium. As you go down that first column, again, the size is decreasing, or the attraction is decreasing. So going down a column, we see the attraction decreasing because the size is getting bigger, less Z effective. Going across every individual row, we see the attraction increasing. Why? Because the size is shrinking, increased Z effective. So the same exact trends as before still hold true. The only difference is now we're measuring it by how they attract a shared pair of electrons, rather than how they attract someone else's electrons or how they hold on to their own. Now, something I should mention here is the way they measure this, it's not something you can absolutely measure. Like with ionization energy, I can legitimately measure how many kilojoules of energy it takes to remove an electron, or a mole of electrons, really. In this case, I can't do that because I'm just looking at a relative comparison. So what they'll do is they'll take the atom who they know is going to have the highest electronegativity. That's going to be fluorine up here, right? And just assign it a value. For some reason, they chose the value of 4. Linus Pauling was the guy who did that. Um, and then from there, take fluorine. If I bond it to another fluorine, they're equal attraction. They should share the electron cloud equally. But what if I bond fluorine to some other element, say chlorine here, that has a weaker electronegativity? They're going to share unequally. We can measure how unequal the sharing is and then calculate what the electronegativity of chlorine must have been compared to fluorine. And then we can do it for other elements and right down the line get values for every element. But you'll notice the very first one, fluorine, we just kind of had to make up. So this next slide I kind of like, and I stole this from one of my professors. It shows by the height of the column what the electronegativity is. And you can clearly see, say, going down the halogen column, as you go down the column, the size of the electronegativity is decreasing, just like we talked about. We won't talk about this column here. Like I said, the trends are not absolute. There's exceptions. Okay? Notice going across a row, the general trend is the value is increasing. Notice again in the transition metals you get some weirdness, but we've come to expect that. But in general, you increase going across a row, you do decrease coming down a column. Now notice on this they put hydrogen over here. Hydrogen's always weird. Remember, it's always our exception. Its electronegativity is 2.1. Now, you'll see fluorine was the highest at 4. Non-metals tend to have electronegativities, 2 and up. Metals tend to have electronegativities sometimes less than 1, but generally 1 point something or whatever. Sometimes they get a little higher. So hydrogen, while yes, it's an alkali metal over here, as far as electronegativity goes, it kind of is an honorary non-metal. But we've come to expect weirdness from hydrogen. Notice also phosphorus has a 2.1 electronegativity. So if you're just comparing general trends, who's bigger than who, a general rule of thumb is pretend hydrogen is right here where phosphorus is. And so you can see if you're comparing hydrogen to silicon, hydrogen's higher. That's, again, a general rule of thumb. But when you're doing electronegativities, pretend hydrogen is sitting right here along with phosphorus. Now, we'll leave that alone for a second. And now that we know about electronegativity, I want to do some artwork here. Imagine I have, let's say, a chlorine atom. There's its 7 dots. And another chlorine atom. There's its 7 dots. Notice they share an electron cloud they share those 2 electrons right in the middle there. That's the covalent bond right there. Now, yes, we draw the covalent bond right in the middle, but in reality, the electron cloud is surrounding both atoms. Now, the electronegativity of chlorine is, let's go back to it here. The electronegativity of chlorine is 3.0. So, 3.0 for this one, 3.0 for this one. It's a terrible 3. What does that tell you? Well, they're the same electronegativity. Subtract them and you get 0. Okay? That's the key to determining what a bond is like. It's not the electronegatividity of the atom itself, it's the difference in electronegativities between 2 atoms. And the more similar they are, the more even the sharing is. So notice they have the exact same electronegativity, a difference of 0. They're going to share perfectly equally. The electron cloud will be evenly distributed around the entire molecule. That's a covalent bond. That's a covalent bond. Now, consider a very, very extreme case over here where I take a sodium atom with 1 dot and react it with a chlorine. Okay? Now, right there's the bond we form. And for the moment, we're kind of pretending it's a covalent bond, right? But let's look at the electronegativities. Sodium is 0.8. Chlorine is still 3.0. If I subtract those, I get, let's see here, what is it? Let's see, 1.2. 2.2. So that's a rather large value on a scale of 0 to 4. That's a rather large value. It's large enough that when they try to share the electrons, chlorine is pulling them more strongly its way. So strongly, in fact, we pretty much say, well, there's the electron cloud. Chlorine gets them all. Sodium gets nothing. Why? Because its electronegativity is so weak. Back over here, they were equally strong. Both sides were pulling equally, and they had to share equally. Here, they're so uneven in their strength that chlorine just takes all the electrons effectively. And that is an ionic bond. Now, what if we go somewhere in the middle? Take a hydrogen bonded to a chlorine. 1 electron for hydrogen, 1, 2, 3, 4, 5, 6, 7 for chlorine. Again, there's the bond in the middle, right? Now, hydrogen we established was 2.1 minus chlorine 3.0. The difference there is 0.9. Okay, so now that's a much smaller difference from over here, so it's not going to be an ionic bond. It's going to be covalent. They're going to have to share. Another way to say that is, yes, chlorine's stronger than hydrogen, but not strong enough that it's going to just be able to rip the electrons away. Hydrogen can hold on to its own. But it's going to be an unequal sharing. So what you end up with is the electron cloud being distorted. Okay, much more electron density over here by the chlorine, less over by the hydrogen. The electrons are pulled toward chlorine and away from hydrogen. So it's a covalent bond. They're sharing electrons. But you have a extra electron density over here, so we'll draw that as a slight negative charge. If you remember that notation from way back when we did water in solutions. Over here you have a slight positive charge. So it's a covalent bond. They're sharing electrons, but they're sharing unequally, and you get an unequal charge distribution. So that molecule will have a slight positive end and a slight negative end, just like water molecules had when we talked about before, because they have these kind of bonds. We call that a polar covalent bond. Okay, because we say that it's a positive and a negative pole. So what determines what kind of bond you have is the difference in electronegativity of the two elements. If their difference is very small, in this case it was 0, you got the true covalent bond, or a non-polar covalent bond, we'd say. If the difference is moderate, you're going to have a covalent bond but unequal sharing, so a polar covalent bond. And if the unevenness is very large, then you're going to have an ionic bond. Okay, so how do you know what the cutoffs are? Well, the cutoffs are kind of arbitrary, but in general, taking a whole scale of electronegativity difference from 0 up to the maximum you can get, which is going to be under 4, but I'll use 4 as my max here. Somewhere right in the middle, you have the cutoff between covalent and ionic. And that's generally considered to be about 1.7, although again, it's kind of wishy-washy. If your electronegativity difference is above 1.7 all the way up, you have an ionic bond. If it's below 1.7, you have a covalent bond. But is it polar or not? Well, the only true nonpolar is 0. But if you have fairly small difference, say if you're below 0.4 is the cutoff we often use, we have a nonpolar covalent. And if you're between 0.4 and 1.7, it's still covalent, but it's polar covalent. Now, be aware that those are arbitrarily chosen cutoffs, and there's all kinds of exceptions. Hydrogen fluoride ends up somewhere up in here, but it behaves like a polar covalent bond, so we call it that, even though our numbers would disagree. So again, these are general trends, not absolute truths. Just be aware of that. So that's it for today. I'm going to let you practice a little of this tonight, and then we'll move on and play a little bit more with this so-called bond character. All right, have a good night.